You study LLMs, they handle isolated tasks, QA, translation, simple stuff. You add tools, WebGPT browses, synthesizes, stumbles forward, you push further. Deep research agents emerge: OpenAI DAR, Gemini DAR, Grok Deep Search. You define them: LLM-powered, dynamic reasoning, adaptive planning, multi-iteration retrieval, tool use, structured reports. You compare to RAG. RAG fixes facts but stalls on reasoning. You compare to tool use systems. They cling to predefined workflows, no flexibility. You build a taxonomy: static versus dynamic workflows. Static, rigid pipelines, one-size-fits-one tasks. Dynamic, LLM planned, evolving with context. You split dynamics: planning only, intent to planning, unified intent planning. Single agent versus multi-agent. Single, one LRM, all-in-one reasoning loop. Multi, specialists, coordinated, scalable. You add memory, extend context windows, compress steps, external storage. No more token prison. You tune beyond prompting: SFT hone, search, report writing, tool use. RL refines with rewards, retrieval relevance, reasoning depth. GRPO outperforms PPO, faster, sharper. You add non-parametric learning. Agents adapt via external memory, workflows, tools. No weight updates, just evolution. You test benchmarks, QA suites, task execution tests. They reveal gaps, narrow scope, static data. You list challenges, broaden info sources beyond browsers, APIs, into the hidden. Fact-checking via cross-validation, self-reflection. Asynchronous parallelism, escape linear chains. Tool-integrated reasoning tools as reasoning partners, not just buttons. You look at the sum. It's not a search agent, not a tool jockey, not a report writer. You build a bridge between human curiosity and the endless evolving ocean of knowledge. A bridge that thinks, adapts, digs deeper, no matter the question.
Okay, let's unpack this. You just heard the frantic, maybe caffeine-fueled journey that AI research has been on lately. It's kind of like we started with these, cute little chatbots, handed them a single task, thought, oh, how quaint.
Yeah.
Right, but the second we asked them to do anything really complex, anything needing sustained thought or, well, learning something new without completely melting down digitally, the system was basically ready to crush, just fall apart. And that's where these deep research agents burst onto the scene.
We had to invent dynamic reasoning, adaptive planning, throw every tool we could find at them. Otherwise, the whole digital house of cards, it would just collapse. It feels less like making AI smart and more like, well, desperately trying to keep it from imploding under all this real-world information overload.
It's actually fascinating how quickly the limitations of those earlier models forced this whole cascade of innovation. Each aha moment, like you said, was really a direct response to a pretty fundamental bottleneck. If we connect this to the bigger picture, it's really about shifting from models that just answer simple questions to agents that can truly research, dynamically engage with a problem, learn as they go, and produce structured insights, much more like a human expert would.
So, okay, let's get specific. When we say deep research agent, what are we actually talking about? It sounds like way more than just a souped-up search engine.
Precisely. A deep research agent, or DR agent, it's an AI system. It's powered by a large language model, an LLM, but it's specifically engineered for these complex, multi-turn informational research tasks. Think of them as integrating several key capabilities. There's dynamic reasoning, which is basically thinking on their feet, then adaptive long-horizon planning, making a long-term strategy and changing it as needed. Multi-hop information retrieval, so pulling info from lots of sources, often needing multiple steps. Also, iterative tool use, using tools repeatedly and refining their approach. And finally, structured analytical report generation, producing these comprehensive, organized reports.
Okay, so they're not just grabbing a few facts and calling it a day then.
Right.
What's the fundamental shift here compared to, say, RA systems or other basic tool use AIs?
Yeah, the difference is pretty substantial. Traditional retrieval augmented generation, RAG, it definitely helped with factual accuracy by fetching external knowledge, but it often, it lacks sustained reasoning capabilities, and it's usually limited by static pipelines.
Yeah.
DR agents, on the other hand, have significantly greater autonomy. They have continual and deep reasoning abilities, dynamic task planning, and adaptive real-time interaction.
And compared to the regular tool use systems.
Right. Those conventional tool use or TU systems were often kind of stuck with predefined workflows, very rigid. DR agents, though, they dynamically adapt how they invoke tools, seamlessly integrating their reasoning with all sorts of multimodal resources.
That's a huge difference. So instead of just fetching a document, they're like interrogating it, combining it with other stuff they found, and actually shaping a whole argument or report. Imagine, for you, the listener, having a research assistant that doesn't just dump a few links on you, but one that actively thinks through your complex questions, figures out the smartest way to get answers, synthesizes it all into something coherent, and adapts its whole approach constantly. That's the kind of leap we're discussing, whether you're prepping for a big meeting or just, trying to satisfy some burning curiosity.
And that core capability, the thinking, planning, iterating it, definitely didn't just appear overnight. It's been, well, a fascinating, maybe slightly chaotic journey of really rapid advancements.
Yeah, tell me about it. Like, before 2020, LLMs were pretty much just focused on those isolated tasks, right? Simple Q&A, machine translation, basic GPT-3 level stuff.
That's right. Those initial models were quite strong for specific, contained tasks, but the ambition was always to push beyond that boundary.
And then 2021, that's when we saw the first real steps towards like pulling in outside knowledge. That's where WebGPT came in.
Exactly. WebGPT was an early pioneer. It started allowing LLMs to actually browse the web and synthesize information they found there.
Yeah.
It was like giving them their first digital pair of eyeglasses, letting them see beyond their internal training data.
That introduction of external tools must have been critical. It really opened the door for them to interact with info beyond just what they were trained on. Real-time problem solving suddenly felt possible.
It absolutely was a turning point.
Yeah.
And then fast forward to 2022, 2023, that's when reasoning really started to connect with action. The React framework was huge for getting language models to sort of synergize reasoning and acting. That paved the way for dynamic single-agent systems. Then came Toolformer, enabling LLMs to autonomously use external computational resources, APIs like giving them a fully stocked digital workbench.
Right, and by late 2023, systems like SelfRag started bringing in iterative retrieval and even self-reflection, like a basic form of thinking about their own thinking. Plus, we started getting those first benchmarks to actually measure how well they were doing on like code and ML tasks.
Yeah, all those developments were really about giving the agents the ability to think through a problem, decide on an action, do it, and then reflect on the outcome. It became this rapid, iterative process. Each new framework was kind of addressing a previously limiting factor.
And then 2024 just felt like an explosion of, well, proliferation and specialization. Suddenly we had DR agents for specific things like Storm for writing Wikipedia-style articles or the AI scientist aiming for automated scientific discovery. The whole field started acknowledging these agentic approaches more formally. Plus, we got tougher benchmarks, right? Like Oswald for real computer environments, our Rebench pitting AI against human experts in R&D, and crucially, those AI-native browsers started appearing designed just for AI control.
That shift from general capabilities towards specialized agents, it really indicates a maturing field. Specific high-value applications are being targeted. And the new benchmarks are absolutely vital. They're pushing models beyond just recalling memorized answers towards true dynamic problem solving in complex real-world settings.
And now, literally as we're talking, 2025 seems like the year the deep dive era really kicks off with all the big industry players jumping in. We've got OpenAI DR with its single-agent approach, Grok Deep Search from xAI mixing real-time info with multimodal reasoning and even credibility checks, Google DeepMind's Gemini DR using interactive planning, asynchronous tasks. It's just, wow, moving so fast.
It is. And what's really fascinating is that clear progression. From basic task handling to these highly complex self-managing research systems, each year really built upon the last, tackling a new layer of complexity, often driven by the very real limits they hit when trying to use older models for open-ended dynamic problems. It's quite a testament to how quickly the field moves.
Okay. So we've traced the why and the where next, but let's get really concrete. What are these agents? Like, fundamentally, how do they actually pull off these deep dives? Let's start with the basics. How do they even get information? It can't just be a simple Google search, can it?
Right, it's more sophisticated than that. They primarily use two main information acquisition strategies: API-based search engines and browser-based search engines. API-based ones interact with structured data sources, think Google Search API, or Civ API, Semantic Scholar API, things like that. Their strength is speed, efficiency, structure, scalability. Great for large-scale data gathering. Like Gemini DR uses the Google Search API for retrieving info across maybe thousands of web pages.
Okay, so that's like pulling data straight from a nicely organized library. But what about the messy, dynamic web that, we use every day? That's where the browser-based ones come in.
Exactly. Browser-based search engines actually simulate human-like interactions. They open tabs, click links, scroll down pages, fill out forms, even execute JavaScript all inside sandboxed browser instances. This gives them much more dynamic, flexible access to all sorts of multimodal and unstructured web content, stuff that's deeply nested, stuff APIs just can't reach. For example, Manus AI's browsing agent runs a sandboxed Chromium instance for each research session just to navigate those complex web environments.
That sounds incredibly powerful, but also maybe slow, like actually waiting for pages to load and scripts to run.
You're perceptive, yeah. They can definitely incur greater latency and use more resources. It's a trade-off. That's why many advanced DR agents actually use hybrid architectures, kind of getting the best of both worlds. And a really exciting development now is the rise of AI-native browsers. These are built specifically for programmatic control. They offer things like stable structured DOM views, explicit API hooks, and even integrated vision language models to handle things like anti-bot challenges, basically making browsing faster and more robust for the AI.
That makes a lot of sense. Okay, so they've got the info. How do they actually process it and extend their own capabilities? What's in their toolkit?
Right. This is where their modular tool use frameworks really come into play. First, almost all DR agents embed a code interpreter. This lets them execute scripts, usually Python or maybe Java utilities, for things like data processing, verifying algorithms, simulating models. Second, they have data analytics modules. These transform the raw stuff they retrieve into structured insights, summary stats, visualizations, quantitative evaluations. CoSearch Agent, for instance, uses SQL-based queries for this.
So they're not just finding data, they're actually analyzing it. Like a little digital data scientist. What about different kinds of data, though? Images, videos?
That brings us to multimodal processing and generation. This is key. It allows them to integrate, analyze, and even generate heterogeneous data, text, images, audio, video, all within one unified reasoning pipeline. The leading commercial agents like OpenAI DR, Gemini DR, Grok Deep Search, they all support this now. It really enriches their understanding of what they can output. And then, probably the most advanced capability is computer use. This lets agents autonomously interact with web environments, execute code, invoke external APIs for really sophisticated real-world tasks. Zippo AI's AutoGLM rumination, for example, can seamlessly integrate its reasoning with authentic browser interactions to access things like user-authenticated resources.
Wow, that's a serious toolkit. But having all those tools must mean they need a really good plan, right? How do they actually orchestrate the whole operation? Are there different sort of blueprints for how they work?
Yes, absolutely. There are distinct architectural workflows and planning strategies. Broadly, we can split workflows into static versus dynamic. Static workflows, they rely on predefined sequential task pipelines. Think of the AI scientist for scientific discovery. They're easier to implement, maybe, but they lack generalization. They're kind of one size fits one.
And dynamic workflows are the opposite, I guess. More flexible, adaptive.
Exactly. Dynamic workflows support adaptive task planning. They reconfigure themselves based on iterative feedback and the evolving context of the research. Most of the advanced DR agents, including Grok, use these dynamic approaches. They just offer superior generality and adaptability. Now, within those dynamic workflows, we see different planning strategies for how the LLM figures out user intent. Some are planning only. They just generate a plan directly from your initial prompt. Grok does this. Others are intent to planning, like OpenAI DR. They actively try to clarify your intent first, asking you targeted questions before making the plan. And then there's unified intent planning, which Gemini DR uses. It generates a preliminary plan and then interactively checks with you for confirmation or changes.
Huh. So some are like, here's my plan, take it or leave it.
Yep.
Others are like, okay, tell me more first. And others are, here's what I'm thinking. What do you think?
Interesting. And what about the single versus multiple agents thing? Is it one super brain doing everything or like a team of specialists? That's another really crucial distinction within these dynamic workflows. Single agent versus multi-agent systems. Dynamic single-agent systems integrate everything planning, tool use, execution within one unified large reasoning model, or LRM. It's all streamlined into a single cognitive loop. This allows for direct end-to-end reinforcement learning optimization, which is good, but it puts significant demands on that single model.
Right, one highly capable brain doing all the heavy lifting. But for really big, complicated research tasks, it feels like maybe a team would be better.
And that's exactly where dynamic multi-agent systems come in. They leverage multiple specialized agents. These agents collaboratively execute subtasks that are dynamically assigned by a central coordinator agent. OpenManus is an example here. These systems are really well suited for complex, parallelizable tasks. They enhance flexibility and scalability, although coordinating all those agents effectively is, well, complex in itself. And optimizing them with RL end-to-end is still a major challenge.
Okay, got it. So we have how they get info, the tools they use, how they plan it all out. But when they're doing these massive deep dives, they must be handling just tons of information. How do they avoid getting lost in that token prison we hear about, or just losing track of what they were even trying to do?
That is absolutely critical, and that's where their memory mechanisms for long context optimization come in. These are vital. One approach, the most intuitive one maybe, is simply expanding the context window length, allowing the LLM to process more tokens at once. Google's Gemini, for instance, supports up to 1 million tokens, which is huge, but this can get computationally very expensive very quickly.
So just giving them a bigger short-term memory, essentially. What happens when the information still exceeds even that huge window?
Then they often resort to compressing intermediate steps. They'll summarize or compress the reasoning steps they took or the documents they retrieved just to reduce the token count. This is efficient, token-wise, but it does carry the risk of losing important details in the summarization. Probably the most robust approach involves utilizing external structured storage for temporary results. This lets them persistently store vast amounts of context way beyond the immediate limits of the LLM's context window.
Ah, like offloading stuff to an external hard drive for long-term memory access. How does that work in practice? What kind of storage?
They use various implementations. Simple file systems are actually quite popular in open source frameworks like Manus and OWL just for storing intermediate results. Vector databases are also used quite a bit by systems like WebThinker. They allow for scalable memory and really fast lookups based on semantic similarities. And then there are even more advanced approaches using semantically structured memory. Things like knowledge graphs or even simulating academic repositories like Agentarchy for collaborative knowledge sharing among agents.
Fascinating. So they have these complex ways to remember and organize vast amounts of stuff. Now, how do we actually make them better? Beyond just giving them good prompts. You mentioned tuning beyond prompting. What does that involve?
Right. Moving beyond just basic prompting is absolutely critical if you want to overcome performance ceilings. There are basically two main parametric tuning methodologies, plus one non-parametric approach. First, there's supervised fine-tuning, SFT-based optimization. This involves training the LLM on carefully constructed data sets that have diverse supervisory signals. Things like telling it which retrieval tokens were good, which results were relevant. This helps hone its search query formulation, its report writing, its tool use. It enhances retrieval quality and helps mitigate hallucinations.
Okay, so that's like showing them tons of examples of good research steps and outcomes. But it still sounds a bit static, maybe. What about more dynamic real-time learning?
That leads directly to reinforcement learning, RL-based optimization. RL directly enhances an agent's adaptive capabilities and its ability to generalize by learning from real-time reward signals. The agent learns, through trial and error essentially, to formulate effective search queries, determine the optimal timing for invoking tools, and so on. This significantly strengthens iterative retrieval, dynamic tool use, and integrated reasoning. PPO is a common algorithm used here, but the research also highlights group relative policy optimization, GRPO, as potentially faster and sharper, giving better results.
Interesting. So SFT is kind of like classroom learning with the textbook, and RL is more like learning on the job with continuous feedback. And you said there's a third way, a non-parametric one.
Yes, non-parametric continual learning. This is often exemplified by something called case-based reasoning, or CBR. Here, the agent refines its capabilities at runtime by optimizing its external memory, its workflows, its tool configurations through continuous interaction with the environment. And crucially, it does this without updating the internal model weights of the LLM itself. It's a very scalable approach with minimal computational overhead during runtime. CBR basically retrieves, adapts, and reuses successful, structured problem-solving trajectories from an external case bank of past experiences.
Wow. Okay, that raises a huge question, though. With all these really sophisticated internal mechanisms, the planning, the tools, the memory, the tuning, how do we even begin to evaluate if they're actually working properly in the real world? And what are the big hurdles still remaining?
That is the million-dollar question, isn't it?
So yeah, what does this all mean for how we measure success? And what's next? It can't be as simple as just checking a box, right?
No, definitely not. Evaluating DR agents is really complex. We do use question answering benchmarks or QA benchmarks. These range from, single hop factual queries like PopQA up to multi-hop reasoning like HotPotQA and even expert level scientific questions. But there's a critical limitation here, something called parametric knowledge hacking.
Parametric knowledge hacking. Sounds sneaky.
It kind of is. A lot of the content from these benchmarks is now just embedded within the LLM's parameters because they've seen it so much during training. So the agent can often answer correctly directly from its internal memory, completely bypassing the actual research process we want to test. It inflates their performance scores.
Whoa. So they're not really researching in those tests. They might just be remembering the answer. That seems like a massive problem for evaluating a deep research agent.
It absolutely is. And it really highlights this urgent need for different kinds of benchmarks. We need open web, time-sensitive benchmarks like BrowseComp, ones that filter out easily memorizable content and truly force the agents to locate hard-to-find, real-time information online. Then there are also task execution benchmarks. These try to evaluate the integrated capabilities tool use, environment perception, through end-to-end research tasks. GIA is a notable one here, often called the most important benchmark, because it offers diverse, realistic tasks that are easy for humans but still really challenging for current agents.
Okay, but even those sound like they might not capture the full picture of what a DR agent is supposed to do.
You're right. Even these task execution benchmarks often collapse open-ended research workflows into narrowly scoped QA prompts or rudimentary GUI control tasks. They tend to overlook the defining outcome we actually want, that structured, potentially multimodal research report, complete with text, tables, figures, citations. It underassesses key competencies like evidence aggregation and cross-modal synthesis.
So, okay, given those evaluation challenges, what are the biggest current limitations? Where do those system-will-crush threats still lurk for these advanced agents?
The challenges are still pretty significant. First off, there's the limited breadth and depth of information sources. Current agents are mostly confined to publicly available web content or static knowledge bases. They generally can't access information hidden behind applications or proprietary interfaces like, say, a Bloomberg terminal. Overcoming this really requires developing more granular and extensive range of modular tools, perhaps through things like multi-agent collaboration platforms or MCPs.
Right, so they can't peek into all the hidden corners of the internet or access private company data yet. That's a huge blind spot for deep research. What else?
Next is the inefficiency and robustness of execution workflows. Most still rely on fairly linear task planning, which just isn't efficient for complex tasks with lots of interdependencies. We really need to move towards asynchronous parallel execution, maybe using structures like directed acyclic graphs or DAGs, and potentially learn scheduling agents to escape these rigid linear chains. Then there are tool-integrated reasoning, TIR challenges. It's not just about invoking a tool. The agent needs to intelligently adapt its reasoning pathways based on the intermediate results it gets from the tool. And the consensus seems to be that reinforcement learning with fine-grained rewards is crucial to enhance tool reasoning abilities.
Okay, so it's not just about using a tool, but knowing how and when to use it in a truly smart, adaptive way. And we already talked about the benchmark misalignment problem. What about those multi-agent systems again? Are they harder to optimize properly?
Yes, that's another point. Parametric optimization of multi-agent architectures is still a tricky area. Most end-to-end RL work has focused on single agents. Trying to do effective end-to-end training and coordination in complex multi-agent systems is, well, complex. Solutions might involve things like hierarchical reinforcement learning or having RL-based dedicated scheduling agents just to manage the team. And finally, underdeveloped self-evolution methods remain a challenge. While we see initial attempts like case-based reasoning via shared repositories like Agent Arikov, the paradigm is still pretty limited. We need more comprehensive frameworks.
Those are some serious hurdles to clear. But looking ahead, what are the most promising future directions? How do we build an even stronger, more reliable bridge to that ocean of knowledge?
Well, the roadmap is becoming clearer. First, we absolutely need to broaden information sources. A big focus here is on those AI-native browsers designed for programmatic control. Second, we have to enhance fact-checking and trustworthiness. Implementing structured verification loops and self-reflection is key. Grok Deep Search's multi-source cross-validation is one example. ZPU AI's rumination model for introspection is another. Third, achieving asynchronous parallel execution is vital. Shifting away from linear planning towards these parallel architectures using DAGs and learned scheduling agents, likely trained via RL. So, giving them better eyes and ears, a stronger internal compass for facts, and the ability to multitask way more efficiently. Makes sense. Precisely. Also, we must continue to advance tool-integrated reasoning, TIR, developing RL frameworks with really fine-grained reward structures that evaluate not just if a tool was used, but how well it was selected, parameterized, and how efficiently it contributed to the reasoning. Addressing benchmark misalignment is ongoing, developing continually refreshed, open web, time-sensitive benchmarks, and also benchmarks that assess the quality of the final comprehensive report. We need to optimize multi-agent architectures through techniques like hierarchical reinforcement learning and dedicated RL scheduling agents. And finally, the longer-term goal is to realize self-evolving language model agents, really expanding things like case-based reasoning, maybe leveraging hierarchical experience traces, and potentially applying evolutionary algorithms to let agents dynamically refine their own execution plans over time.
It's really fascinating. The challenges aren't just about tweaking existing things, are they? It feels like it requires fundamentally rethinking how AI interacts with information, how it learns, maybe even how it collaborates with itself or other agents, which I guess raises that big question. How much of this deep research capability will eventually become indistinguishable from, actual human intellectual work?
That is indeed the profound question looming over the field.
Well, from those early kind of isolated LLMs to these incredibly dynamic deep research agents, we've definitely seen a massive leap. From simple task doers to sophisticated knowledge explorers, it really feels like that bridge is being built, connecting our human curiosity with this vast, constantly evolving ocean of knowledge. A bridge designed to think, adapt, and dig deeper no matter what question you throw at it.
It's an exciting frontier.
So here's a thought to leave you with. As these deep research agents continue to evolve, integrating maybe ever more deeply into our whole knowledge ecosystem, what new forms of human curiosity and inquiry might they unlock? Things we can't even really conceive of today. What questions will we finally be able to ask and get meaningful answers to that were simply unanswerable before?